Okay. Hello. Hello. Hello, hello. Long time no see. Long time no see. I miss you. Good afternoon, Alfred. Thank you for the good afternoon. All right, now we're happening. Oh, sorry. Yeah, thank you. I appreciate. Hold on one second. Yes, thank you, Alfred. No, I'm very good. I mean, I look different. Clearly, I'm looking more and more, but I'm great. Thank you very much. I just missed you guys. I'm sorry to be missing so much. The schedule is crazy, and I'm making it crazier. But no, it's all good. Thank you for the kind thoughts, Alfred. Hello, Brandon. Good afternoon, Sydney. Good afternoon, Yaneli. Good afternoon, Samantha. Good afternoon, Kaya. Good afternoon, Ariana. Good afternoon, Genesis. Good afternoon, Brian. Good afternoon, Erica. Good afternoon, Matthew. Good afternoon, Doran. Good afternoon, Gabriella. How nice. Very nice to see you. Nice. Oh, and I love Alfred. Oh my God, Alfred's avatar is like cray cray. Okay. And Brian's totally counts as an avatar, as of course does Yaneli's. Good to see you all. No, I really do miss you. I mean, the spotty, I'm not helping our schedule. It's been so long since we've seen each other. I am not helping our schedule at all, but neither are all the holidays. Um, Whoops, sorry, not what I meant to do. Yikes, happened. Okay. Um, 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 um. Oh, more people coming. Okay, 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 okay. Um, 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 um. Okay, so it's been a long time since we've rocked and rolled. Um, we have some physics to do today for sure. There's been a lot. The physics has been piling up, as you've noticed. The homeworks have gone longer, harder, but you guys are doing an amazing job. It's clear. I think. Well, no, no, no. I mean, I know you were doing an amazing job. That's not the I think part. Okay. I want to like just do some bookkeeping, some quick loose ends, and then get to some physics here. So, like, you've been asked to do a lot of the learning from past videos and from Professor Liu and all that kind of stuff. And what I can tell from all of especially from the questions that you submit and the comments that you submitted about the videos, you're making it very helpful to me to see where you're clear and where you're not. Like, and it is clear that you are keeping up with the work. Like you are clearly keeping up with the work, and that some of the stuff is confusing and we need to talk about. That's for sure. But many of you are doing a very good job of making a clear distinction between what you understand and what you don't, which is the big part of figuring out physics. Um, and again, I hope you notice that the policy remains the same. Like as long as you hand in some kind of valiant first draft for a homework in time for the due date, as long as you hand in a valiant first draft, then even if you don't get all the points right away on that first draft, you eventually can get all the points as long as the first draft comes in on time. And when that first draft comes in, as many of you notice, sometimes you get feedback right away. Sometimes you just get a bunch of points as an acknowledgement that you've made an attempt. So if you just get a bunch of points, but not all the points, that means I think it's either that we both know that you're still missing stuff or that things are going to get clarified in class. And then you're going to hand in the rest and get the rest of the points. Like if you get a big bulk of points right away, it just means, yes, I see that you're totally doing the work and you're on top and you're not done yet. And great job. And you're going to get all the rest of the points as once, you see what to do in class, et cetera, et cetera. Or in the case, just to remind you, sometimes if you hand in an amazing thing right at the first draft and you actually do everything and you think that you nailed it all, but I just went too quickly and didn't give you all the points and I didn't give you any feedback. Once we go through class and we do everything and you still think, wait, I did everything and I did it all correct. I don't even know what the issue is here. Just turn it in again. Just literally take the same document. Don't trouble yourself and just say, please recheck this, professor. I think everything is there. And that might well be the case. And then you'll just get all the points. Right. But sometimes you get a lot of feedback at first, or you'll get the feedback later. What I'm trying to say is I feel like you guys are on top of the work and you're staying on top. And I feel like everybody who's done everything that you've done so far, I feel like you've gotten something back for, whether it's points or feedback or both. So keep it up. Basically, I'm just saying keep it up. And what I can tell by looking at all your work, what I can tell is that I don't want to waste your time. I am now not going to go through problem by problem and redo all the problems that you've already seen in the videos or already discussed with Professor Liu. What I am going to do today, the main thrust of today, the one problem that is most important, that's worth us all looking at together in real time, is the actual big old duck problem. Oh, and thank you very much, Gabriella, for the kind words. Yes, I'm glad to see you too, if I didn't already acknowledge. No, I'm very, really, it's keeping me healthy when I see you guys. So the big problem that we're going to walk through today as a group, I'm going to screen share it just so it's clear to everybody. Hold on. And then you can screenshot it if you, I mean, I think everybody has been thinking about this for a while, but in case you're, so hold on. So what we're talking about today is this, right? Right. Couple of, so, and we're going to spend the whole period today walking through this. So I want to make some comments as to why and what to look for, even though I know you've already seen it in a video, but you've seen a lot in the videos. I'm not going to be redundant about everything, but this one is worth reviewing clearly and making extra comments about and all of that for a number of reasons. Okay. Number one, again, I've looked at your homeworks. I've looked at your video comments. And even when I don't comment, I'm reading it all. So I know that a lot of you still have very legitimate questions or concerns about this one. Like you might now have the answers, or you might now know things that you didn't know before. But a lot of you still are confused about certain parts. So it's worth walking through. A lot of you still want to get all the rest of the points on this. So it's worth walking through. That's number one. Number two, to be super clear, this is the last big problem that closes down the topic of one-dimensional kinematics. I'm going to put this in the chat. People asking there. Like the topic that we've been doing all the while until this point. Whatever. Okay. If you were ever trying to look up everything that we've been doing so far, if you were trying to look up extra enrichment or help through Khan Academy videos or through textbooks or other online resources, what you're looking up, what we've been doing is one-dimensional kinematics, motion within a line, and or the nature of constant acceleration. All the equations, all the concepts, all the laws that we've been doing is physics as it takes place in one dimension with constant acceleration. So those are like your search terms on Google or whatever if you're looking these things up. And the big old duck is the last big problem that puts together pretty much like so many of the details and the concepts from this topic. Okay. Um, it it transitions us to the next topic that you already started in lab and you started in the videos, but we haven't started discussing in real time, which is two-dimensional kinematics. So the big old duck is the transition from the first topic to the second topic. Therefore, the big goal, and it's a big, hard, challenging problem. It is challenging. It's meant to be challenging. Arguably, it's like the hardest, biggest problem we've had so far. It, as I've mentioned before, but I want to reemphasize, it almost always appears in some form on the first exam, which we'll talk about the exam soon. We'll talk about it Wednesday, in fact, with the dates and all that. But when we have a midterm exam, there will be a problem on the exam that will be conceptually the big old duck. It won't look like the big old duck necessarily, like it won't mention duck, but it will be the same problem solving. Like you'll have to know how to do the duck in order to do that problem. So it's very worth practicing and knowing the big old duck. Also, the big old duck basically is lab 3 and lab 4 in different disguised formats. So if you can ultimately see how lab 3 and lab 4 and the practice exam problem all are different versions of practicing this big old duck, then you really are understanding the physics that we need to understand so far. And it's why it's worth unpacking the big old duck and knowing it well. So we're going to walk through it carefully today. Hold on, my screen is all messed up. Pardon me for a second. Right. So this is the problem that we're going to walk through today. I'm going to try to say things about it that I don't necessarily say in the videos, so I don't want to waste your time. Number two, I really want you to stop me. I want you to pay close attention to, obviously some of it you now get, but some of it you still don't. So pay attention to the parts you still don't get, or the nuances or the subtleties, and ask me about it while we're doing this in class. It's all we're going to do today is trying to look at all the different concepts through the big old duck. The other thing two other things I want to warn you is, one, when I walk through in the video, someone pointed out in the other class, actually, when I walk through it in the video from the past semester, evidently, I don't know this for a fact, but I believe it. Evidently, even though I walked through it slowly and everything at the beginning in the video, at the end, I made some kind of mistake or something and ended up doing a wrong computation at the end and getting the wrong answers in the old video. And that may be confusing some of you or misleading some of you. I didn't realize that until someone just told me an hour ago. So the other reason to pay attention today is I'm going to walk through the same problem and all that, but I'm going to get the answers correct today. I promise you they're correct today. So compare what I'm doing today to what you ever saw in the videos and see where I'm correcting the answers. That's a reason to pay attention, if nothing else. And finally, let me say that if you're so sure that you're totally solid on this big old duck problem, like you've now watched the video a million times, you corrected your homework, you got full credit on the homework. If you're that confident, and I don't think this applies to that many people, and I think you should be careful about being overconfident at this point in the semester, but you've done this a million times in high school or something, if you're really sure that you're down with this big old duck, then what I would say is, since it's going to be on the exam, my recommendation so that I don't waste your time this period is, if you're really sure that you're solid on it and you even already know where I went wrong in the video, then take all the numbers in the big old duck problem that you're seeing right now. Sorry, my screen is so messed up. Sorry. Wait, I'm going to stop the share just because if I'm about to start walking through the big old duck problem, and I'm going to screen share the normal screen, but if you're so sure that it's going to be a waste of your time, then don't leave the class. What you should do is take every number that's given in the big old duck problem and just double it. Like, take all the given values, double them, and mute me, and take out a separate blank sheet of paper and solve the big old duck fresh yourself with doubled values, like without looking at your other work, without looking at your homework, without listening to me. Just do it as a practice problem for the exam right now. And I'll open up a portal, especially if someone reminds me. I'll give you extra credit for doing it if you hand it in cleanly, like as another practice problem. If you think that would be more worth your time today than actually listening to me doing it, because people are always asking for more practice, just double all the numbers, all the given values, and solve it without looking for practice. I hope that's clear. If it's not clear, let me know in the chat. But other than that, I'm going to walk through the big old duck now with everybody and get the correct answers and try to say insights about it that I haven't said before. So bear with me. I'm going to share the other. Okay. So here's the board. I'm going to switch the screen too. Notice we usually have an equation on the board, right? We usually have like the new equation of the day or the new equation of the next hour, the old equation. Notice even today, to start this, I'm not even giving you a new equation. I'm reminding you of something that was in one of the videos of the fifth form of Galileo's principle of relativity. Again, let me emphasize Galileo's principle of relativity, which is really what this is all about, is one principle. We keep saying it in different forms. Every time we get to a new subtopic in the class, we're embracing or extending a new version, a new form of this one principle of relativity. The forms are getting more and more mathematical and more sort of directly usable. And many of you said in your responses to the videos that, like, for example, with GPR form number 4, which is this one here is number 5, but there was a whole video about GPR form number 4, which is where things start really looking mathematical, VAB plus VBC, etc. And many of you are very wisely saying in your responses to the videos, like, okay, I think these GPRs are making sense, but I really need to see how they're concretely applied. I really need to see them in action in order to know if I'm really making sense of them or not. You're absolutely right. Yes, we need to see them in action. We need practical, concrete applications of them. And today, we're going to see a concrete application of GPR form number 5 in action. Form number 4 is a different thing. It applies to other aspects of that homework sheet, but not this problem. Today, we're going to see GPR form number 5 in action. What does GPR form number 5 say in English? It specifically, what it's really saying is we don't need new equation. It's saying that even when you look at a problem that looks like a two-dimensional problem, like we have this duck problem where something is being fired up along a y-axis and some duck is moving horizontally along an x-axis. It looks like things are now happening in 2 dimensions. Just like in lab number 4, you have something being fired off a table and it's moving along a horizontal axis as it also falls down to the ground along a y-axis. It seems like things are now happening in 2 dimensions. And we say to ourselves, wait a minute. All the equations we ever learned were one-dimensional kinematic equations. We never learned any physics for how to deal with 2 dimensions. And what we say is, no, if we really take Galileo seriously, if we really understand that the laws of physics hold the same in every unaccelerated reference frame, in every single coordinate system, and if we really understand that even an axis is a coordinate system, one axis is the simplest coordinate system or the simplest reference frame that I can imagine, then the laws of physics hold along each axis unto itself. So a way of putting Galileo's principle, a form of Galileo's principle, what we call form number 5, is every experiment, no matter how many dimensions it seems to be occurring in, is really just a series of separate experiments or a collection of a separate experiments. So when I say n here, like n one-dimensional experiments or n-dimensional experiment, n could be any number. It could be 2, 3, whatever number of dimensions we have. Let's take here specifically with the big old duck that we're about to solve. The big old duck looked like a 2-dimensional problem, but the main insight we need to solve this hard problem, it's not that we need new equations. It's that we need to understand how to apply our old equations. We need to understand that even though this looks like a 2-dimensional problem or a 2-dimensional experiment, it is really 2 one-dimensional experiments occurring at the same time, but independently. Now that is not extra words. Every one of those words counts. In the big old duck problem that we're about to solve, the insight is this stuff with the duck is happening while this stuff with the bullet is happening. They're happening at the same time, yes, but they're happening independently, meaning that the laws of physics and the equations of physics are governing whatever's going on here by itself. The shot that is trying to make it to the height of a duck doesn't care or know about the duck. Physics will dictate what's going to happen to this bullet, whether or not there's a duck going on. And similarly, the laws of physics will tell the duck what to do, whether or not there's a bullet happening in the y dimension. So we're saying that each one of these equations that we learned for an axis will apply to an axis and will also apply to an axis, just one at a time. So we deal with each axis of physics one at a time with the equations, the one-dimensional equations that we already have. And then how do we put them together? Well, in this case, we're going to put them together, and then I'm going to turn the page and move to the problem. We put them together by the knowledge that they're all occurring at the same time. So the common factor between the y-axis and the x-axis in the case of the big old duck is that this motion and this motion occur at the same time. So the variable t will be the variable that holds everything together in this problem. So that's the main principle that we're looking at here. But if that's the principle that each axis is going to be treated independently, then we're now going to treat each axis with all the physics that we've learned up until this point, sort of put together in a big package. That's what makes the problem a big sort of review culminating problem. Okay, so this is the principle, Galileo's principle, form number 5. That's the principle we're going to use to solve the problem. Now let's look at the problem. So here's the problem. The big old duck, right? So I'm sort of trying to do it by the step method and all of that. So step 1, there's my diagram, sort of copied off from the problem, more or less. And it's kind of sketchy, but there's the facts and the diagram of the problem. We have a duck up here at a height of 40 meters above a hunter. And the duck is traveling south in sort of a complicated way, while gravity is always pulling down in the way that gravity always does. So those are all the facts of the problem. But now let's be clear about a couple of things. In that diagram, I'm making sure not only to put in my numbers and all of that, but I'm putting some labels. I'm absolutely making decisions about positive signs and negative signs now. Like direction is going to matter. Direction. Oh, hang on a second. There's something. Okay, wait, sorry. Something in a private chat. But one second. Okay. So one thing that's really important in the labeling of my diagram is I'm choosing positive and negative because there is more than one direction occurring in each dimension. Like what I'm trying to say is notice, and this is Galileo now. I not only can I, but I have to make choices about what direction is positive and what is negative. It's up to me, but I have to stick with the choice I make, and I have to make a choice. I can't just let it alone. And I have to do it for each axis. So in the up, down, the y-axis, I'm choosing to call up positive and call down negative, right? You see in the picture over to the left. I'm choosing to call up positive. Anything that goes up is positive. Anything that comes down is negative. Now, a couple of people asked questions about this, like in the video, in the stuff, in the homework. Like you'll notice in some of the videos and some of the other problems, I chose to make down positive. That is often a very wise thing to do. It is a choice. In the problems from the videos, when things were just falling down, when something's only falling down and it's never going up and nothing's going up, I make down the positive direction. That's not what I did here. Notice it's a choice. What's the choice you make to try to make, you're trying to be strategic. You're trying to make your math as convenient as possible. What makes math convenient? Nobody wants negative signs. Negative signs are harder to deal with than positive signs for all of us. A lot of negative signs get confusing. We have to have some to distinguish one direction from another, but you want as few as possible. So if you know everything is going in a down direction, we make that positive. You don't have to, but that's like a convenient choice. What you have to do is make your choice clear. So here, some things are going up, like the shot is going up, but gravity is pulling down. So both directions are going to be taken into account. So I made positive, I made up positive in this case. Again, you could do something different, but you have to be clear and you have to stick to it. But now also notice that's for the y-axis. I make a separate independent designation for the x-axis. I called south positive. I called north negative. Now you might say, well, that's weird. Isn't north usually positive? Often north is positive. But in this case, the duck happens to be traveling south just because it is. It, it just is told to you in the problem that the duck is going south. The duck is going south. It's accelerating south. Nothing seems to be happening, at least at this stage, in the backwards direction. So I just, because I want to minimize negative signs, I made the south direction positive. You don't have to do that, but that's what I did. But you do have to make it clear. And what you have to see, and I'm going to move on now, obviously, but what you have to see is that you make one positive and negative choice for one axis and you make a separate independent choice for the other axis. Each axis is its own coordinate system or world of physics. That's GPR form number 5. Okay, so I've labeled all this. Oh, plus last thing, also I label like my zeros. Like notice in very faint blue, you could see that my y equals 0 is where the shot is fired from. Like that's what I'm calling y equals 0. So everything above it is positive. And wherever the duck is positive 40 meters above that. And similarly, where the hunter starts, I'm calling x equals 0. So strictly speaking, everything to the left of the hunter or everything to the north of the hunter would strictly speaking be a negative sign. Okay, so that's my setup. Is there anything else in the chat? Okay. So now so that's my step 1, my setup. Step 2, what is the question? The question is at t equals 0 second. Well, so it says at t equals 0 seconds, the shot is fired. The question is, how far back is the duck at t equals 0? Or how far back must the duck be if the duck is to be hit by the bullet? If the duck is to arrive at the horizontal coordinate of the hunter by the time the duck gets shot? Like that's really the question, right? It's very much like the question of lab 4. Where must the target on the floor be? Sorry. The question of lab 4 is how far back must the gun have been placed if the bullet that comes out of the gun on the lab table is to hit a target on the floor? This is a very forensic science kind of question. Not what will happen in the future, but what must have happened in the past if a crime occurred in this way, right? We're looking at present conditions of a crime, in this case of a duck being shot, or in the lab of a target on the floor being shot. And we're really asking to unravel the movie of physics to figure out what must have been the preconditions of the crime in order for it to have occurred that way. That's what forensic science is, or that's what criminalistics is. All right, so that's the question. Now, it seems like a very big, hard question. It is a very big, hard question. We're going to have to break the question down into steps in order to solve it. But step 3, GDP, general definitions and principles. Well, I'm saying the general definition or the principle to use to solve, before I even get into equations, the principle here is Galileo's. The principle is things are happening vertically, things are happening horizontally, but what is common to both axes is the time. Time, what it says here, time is what is shared in common by the two axes. Thus, we should solve for the time. We should solve for the time at which the bullet and duck occupy the same position. Like we're looking for a collision here. We're looking for the shot to arrive at the same point in space, at the same point in time as the duck. We're looking for a collision. So what we're really saying is it must take the bullet the same amount of time to go from here to there as it takes the duck to go from here to there. The time must be the same. So we're going to solve for that time. Now, the next insight is, well, which time? I mean, it's the same time, but how can we do that? I'm going to say, let's solve for the time it takes the bullet to go from the ground to the height of the duck. Because if you really understand that the x-axis doesn't affect the y, here's where the word independently comes in. Yes, the y motion is going to occur at the same time as the x motion. But if they're truly independent, that means the bullet doesn't know or care anything about the duck. That means the bullet is just a standard physics problem. The whole purpose of all the other, the first practice problems that you did in the videos and the other earlier practice problems in the homeworks were really about studying, practicing. If you just fire something up, if you throw something up at an initial speed of 30 meters per second, how much time does it take to get to a height of 40 meters? Like the bullet is an independent physics problem that could be solved on its own terms without any knowledge of the duck. So I'm going to do that one first. Yeah, so what it says here on this page, the amount of time, it says the amount of time it will take the shot, the bullet, to arrive at a certain height is dictated by the laws and equations of physics. It is independent of the duck's motion. Now, it's also true that the duck is independent of the bullet's motion. But the bullet is the problem that we've solved over and over again in physics class before we even get to this stage. It involves free fall due to gravity, which we've been practicing to this stage. So I'm going to, so I'm going to solve, so I'm going to look at how much time it takes the bullet to get from the ground up to the height of the duck. That's what this all is right now. I'm going to walk through this right now. But let me say it one more way before I go further. What I'm really saying here is we are now going to solve for the amount of time that the bullet is going to take to get to the height at which the duck is. Like, we're not really solving for anything about the duck. We're just saying the duck is at a height of 40 meters, so we're above the bullet. So we're just solving for how much time does it take the bullet to travel 40 vertical meters. I hope, and if you don't understand that distinction, put it in the chat. But everything I'm doing now doesn't care or know about a duck. It just knows about the physical facts of the y-axis. So I'm saying, I'm using that equation, displacement equals 1 FA squared plus V naught T. And I'm saying I'm applying it, so that's the first line. I'm applying it to the y-axis, the vertical axis of this problem. So I'm now going to make that clear in my mind. Like, again, every equation that we have here, I'm going to use this equation again later on in the x-axis. It's all the same equations being used one axis at a time. But since I'm using it in the y-axis here to make it clear to myself, I'm adding subscripts. It's not to make it more confusing. It's not making it a new equation. It's just to make it clear to myself that I'm applying the equation to the y-axis. So I say y equals 1 FA sub y, like the vertical acceleration, t squared, plus v naught sub y times t, right? And what do I mean by that? So now I'm plugging in further. The acceleration in the y-axis is the free fall acceleration due to gravity, called lowercase g, right? I'm just like, it won't be in the horizontal. There's no gravity in the horizontal axis, but there's gravity in the vertical axis. So I plug in g for a sub y. Again, stop me if any of this is getting and v naught y for, okay. So now I'm moving to step 4. I'm starting to plug in the numbers. And I'm paying attention to my positive and negative signs that I assigned to the vertical axis. Okay, the displacement in the vertical axis, the height that this bullet is going is up. It's going up 40 meters, right? And it's, so that's a positive. So this is a positive 40 meters is the displacement. The acceleration in the y-axis is the acceleration due to gravity. We can round to 10, that's fine. And we're calling it negative. We're not saying that gravity is always negative. We're saying gravity is always pointing down. We're saying gravity is always down. Sometimes we make down a positive value. I mean, sometimes we designate the down direction as positive, as we did in some of the videos, but here we decided to call down negative. So therefore, the acceleration due to gravity is -10, right? But the initial velocity of so the shot is accelerating down, but it was fired up. It was initially thrust at an upward initial velocity of 30 meters per second. So we make that positive. You stop me if that's not clear. So we have plus 40 equals 1/2 -10 t squared plus 30t. All right. So we have one equation with one unknown. The one unknown is t. Now it looks a little intimidating because we've got a t squared and a t. That's a little bit algebraically. It depends how good you are in algebra or in pre-calc or whatever, but that's math, not physics now. So we're solving for the t, the time that it'll take this thing to go up. So so I'm just gonna just simplify the terms like positive 40 equals -5t squared plus 30t. Just looking at the chat. And then I rearrange to make it look like, because it's a quadratic equation now. So I'm making it look like a quadratic equation. I put all the terms on one side, make them all set equal to 0. So I have -5t squared plus 30t plus -40 equals 0. Then to make it even, now you could just apply the quadratic formula if you're careful and you're comfortable with it. You could use a graphing calculator and solve for the two roots on the graphic. That's fine. Or you could do the completing the square, or you could simplify this and divide both sides by -5. If you divide both sides by -5, you get t squared minus 6t plus 8, and that's convenient because then you can see that this is actually not that bad of a quadratic. It's actually a factorable quadratic. So that's the way I did it. I factored. So we get t squared minus 6t plus 8 equals 0. It's factorable quadratic. So you're looking for the two numbers that when you multiply them together would give you +8, but if you added them together, it would get you -6. So -4 plus -2 gets you -6, but -4 times -2 gets you +8. I mean, I just know that from experience, but you can check by foiling. And again, that's if you're good at factoring, that's how you factor it. If you don't like factoring, you can do the quadratic formula, whatever. But you get these two roots, +2 and +4. Now let's pause on this for a second. The math gives you two roots because quadratic equations always give you two roots. I mean, if the highest power of the independent variable is a 2, then you have like a parabola that's crossing the x-axis at two places. So there's two values of x such that y equals 0. Those are the two roots. Like, put another way, anytime something squared, just in the simplest term, if I just said, okay, x squared equals 9, what does x equal? If I say x squared equals 9, what does x equal? Well, you might say 3, but because 3 squared equals 9, but the truth is -3 squared also equals 9, right? That's just a simple example to say, whenever you say something squared equals a certain number, there's always two possible values that when you square them, you would get that number, because positive times positives equal positives, but also negatives times negatives equal positives. So mathematically, whenever you have a quadratic expression, there's always two possible answers. That's math. But physically, that's got to mean something. Like, math is supposed to be the language of the physics. And I'm not saying this is the answer to our whole problem, but I'm saying if we were asking the sub question here, at what time does the bullet arrive at a height of 40 meters? Physically, there are two distinct possible times at which the bullet would arrive at a height of 40 meters, assuming the facts of the problem, assuming that it was shot up at an initial velocity of +30 meters per second, and assuming it was shot up near the surface of the Earth where gravity is always pulling it down and always accelerating it down at a rate of 10 meters per second squared. Assuming all those conditions, there's two physical real times, two physically possible times at which this object would arrive at a height of 40 meters. One time would be on its way up, and the other would be on its way down, right? And I want to emphasize that. I know I said in the videos and all that, but let's be very clear about this. What we are saying is that if you shoot something up at 30 meters per second in near the surface of the Earth, where gravity is always pulling you down at an acceleration rate of 10 meters per second squared, if you shoot something up at 30 meters per second, in other words, if something's moving with an initial velocity that is in conflict with its acceleration, if it's trying to move up while it's accelerating down, or if it's trying to move right while its acceleration points left, or vice versa, if it's moving in a direction against its acceleration, that means that the velocity numbers are going to trend toward zero and then keep going on the other side of zero. I'm saying if this thing is shot up, and I'm saying this has nothing to do with the duck. It has nothing to do with the duck. It's just a bullet being shot up. If it's being shot up at 30 meters per second, it's going to go and go. But it's losing 10 meters per second of velocity every second. Then it's going to go positive 30, positive 20, positive 10, 0. And then if that acceleration is truly constant, which we believe it is truly a constant acceleration due to gravity, so it's going to go 30 at positive 30, positive. I'm not talking about where it is. I'm talking about how fast it's going. Positive 30, positive 20, positive 10, 0. Then it's going to keep losing velocity. How do you keep losing velocity once you're at velocity 0? You're going to go into the negatives. It's going to go negative 10 velocity, which means it's going to start coming down now. Then negative 20 velocity, so it's going down even faster. Then negative 30 velocity, right? It necessarily has to reach a peak height of 0 velocity and then start coming down. Not because of the duck, just because of gravity. So this thing necessarily is going to go up and then come down. So if we're asking when's it going to be at a certain height, as long as it can get high enough to pass that height, it's going to hit that height twice. One its way up and one its way down. And the physics and the math never specified. It just said, when is it going to be at that height? That's all we're solving for. Time to be at that height. So there's literally two. So in other words, when the math gives you two answers, don't just throw away one and say, oh, we're only looking for. No, it depends on how the physics question's phrased. The physics wants to know when it's going to be at that height. There's two possible times to be at that height. 2 seconds would be on its way up. 4 seconds what's going to be on its way down. Now, you should stop me if you're unclear on any of that, because I'm going to say more about it now. That is not the answer to the whole question. That's just the times that the shot is going to be at the height. We need to use those times to solve for the rest of the question. But for those of you especially who basically get this, but really want to see more physics and make sure you fully understand everything and practice and everything for the sake of the exam, let me say now something I may or may not have said in the videos. Let me test that. Let me check that this 2 and this 4 really makes sense. I'm saying here, evidently, the shot will arrive at a height of 40 meters at 2 distinct times. 2 seconds, it'll arrive at 40 meters on its way up. It'll arrive at 4 seconds on its way down. Now, I want to check that that makes sense. So I'm going to do this little sidebar here, this side check. I'm going to ask myself, how much time until the peak height, independent of the duck? Let me pause. Let me tell you what I mean. Because many of you made good comments to me about the videos and stuff in your homework. Many of you said you noticed that in the video, one of the videos, I kept emphasizing that we should try to be logical and conceptual and make sense out of this stuff, even before we start just randomly plugging in blindly into equations, especially with equations that have squares in them. And some of you asked me like, all right, that's cool, but some of you said like, I don't really know what you mean. Like, how am I supposed to be logical with like outside of the equations? Or what do you mean by being logical before I go to the equations? Oh, good question. I'm going to show you right now an example. But one main thing I mean is because I mean, the equations are logical. That's what I want you to see. The equations are not black magic. The equations are supposed to be efficient ways to capture ideas that actually make sense, right? But they start looking more and more, the equations start getting more and more efficient and start looking more and more obscure around now, especially when you have equations like 1f at squared. What I'm really trying to say is, when in doubt, before you start squaring things, before you start plugging into things that have squares or square roots in them, whenever possible, try to bring things back to the simpler definitions and equations of average velocity. All the stuff we were doing at the beginning before things started getting squared and started getting very algebraically complicated. When impossible, try to bring things back to the simpler, straightforward notions of average velocity. That's why we did that first. Average velocity makes more sense to many people than average acceleration. And the average velocity equations don't have squares or square roots in them. So I'm going to say right now, let's try to make sense of this. Do we really believe that this shot really could hit 40 meters on its way up and then go higher than that and hit the 40-meter mark on its way down? In other words, do I have good reason to believe that this shot is even fired hard enough to make it past 40 meters? Like, how do I even know? I'm saying it's going to hit it on its way up. And I'm not saying well, yeah, I am saying. I'm not saying it's going to hit the duck twice. I hope that's clear. I'm not saying anything about the duck yet. I'm just saying that height. I'm saying this shot will pass a height of 40 meters once on its way up, and then it'll pass that height of 40 meters again on its way down, which means I'm really believing that this shot has been fired hard enough to pass 40 meters. I'm saying it's got enough thrust to make it to a height that's bigger than 40 meters. Do I believe that? Do I know that? Like, I mean, how am I so sure that the shot is good enough? How do I know it's not just going up like 15 meters and then coming down before it even gets to the duck? So I'm going to check right now. I'm going to say, hey, this is like a standard physics problem. If you got a shot that's fired in gravity at 30 meters per second, can't we just like figure out how high it would get in and of itself, regardless of ducks? Yes, we can. And we can do it without squares and square roots and all of that. It's a good practice problem for exams and based on all this video stuff. So what I'm going to do right now is I'm going to say conceptually, and we're on time here. So I'm going to just do this in my head. I mean, I'm writing it down, but I'm not using any equations now. So when I'm done with this, you should make sure that you understand. And I don't think I did this in video, but I'm not sure. You can stop me. You should stop me. We have time. We'll get to the end of the problem. And all we're doing today is this problem. So make it worth it for yourself. I'm about to explain something conceptually. You should make sure you see what I'm doing without equations. I'm going to say to you right now, this shot the bullet is fired up at 30 meters per second in gravity. So I believe right off the top of my head, it's going to travel for 3 seconds until it reaches its peak height. It's going to get to a peak height, wherever that peak height is, it's going to get there in 3 seconds. Do you understand that? It's going to get there in 3 seconds. I could show you with an equation, but I want you to start seeing, or if you do think you understand that, see if you could see how to show yourself with an equation. I think it's going to get to a peak height in 3 seconds. Why? Because it's starting with 30 meters per second of velocity and it's losing 10 every second. And a peak height will occur. It'll start coming down once it's run out of velocity. Like at its peak height, it has a velocity of 0 for 1 instant, right? For 1 instant. It's no longer going up through the positive values, and it hasn't yet started coming down in the negative values of velocity. When you throw something up, it goes slower, 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 slower. It momentarily hovers. It does. For 1 instant, it's got no velocity at all. And then it starts gaining speed or, getting increasingly negative velocities on the way down. So So how much time will it take to fully run out of velocity? It will take 3 seconds because it lost 10 every second. See, I'm doing that in my head, and you should be able to also once you get this. Is it an equation? Yes, it's the equation A bar equals V minus V naught over T. In fact, well, yeah, I'm not gonna. You can ask me, and I would encourage you to, if you want me to write it, I will. I just don't want to rabbit hole or crowd this page. But I'm saying A bar equals like triple equal sign V minus V naught over T, and I'm solving for T here. I'm saying A equals -10. I'm saying V equals positive. Excuse me. I'm saying A equals -10. I'm saying V final equals 0. I'm saying V naught equals positive 30, and I'm rearranging for T. If you want to hear that again or ask me, feel free or write it down. But what I want you to see is it conceptually makes sense. We're literally just saying if you have 30 apples and you lose 10 apples a day, how many days does it take you until you don't have any apples anymore? And the answer is 3 days, right? So that's an analogy. But so this thing is going to run out of speed in 3 seconds, definitely. I can go a step further now and say, well, if it's going to run out of speed in 3 seconds, it's going from 30 meters per second to 0 meters per second in those 3 seconds, then its average velocity is 15 meters per second. I'm doing it in my head. You can too if you know what to do. This is the other equation. V bar equals V naught plus V over 2. I'm saying this is all constant acceleration. So all of our constant acceleration equations apply. It starts at velocity 30. It ends for this segment at velocity 0. It's constant acceleration the whole way. So its average is the average of 30 and 0 divided by 2, 15. So this is like some object just traveling at an average velocity of 15 meters per second for a total duration of 3 seconds, right? This, in effect, is an object going 15 meters per second on average for 3 seconds. So it's like a car going 15 miles per hour for 3 hours. How far would that car get? It would get 45 miles. How high does this thing go? 45 meters. We're doing that in our head. Does it relate? Could you use all the equations? Yes. Does it express all the equations? Yes. We're not making crap up. But I'm trying to show you that the equations are just capturing logic that actually makes sense. And what do I mean by logic? I mean the logic of average velocities, really, is the logic that the definite, it all comes down to average velocity is defined to be displacement per time. So what this page says, so what I'm saying, but please, in fact, I'm a little, I'm going to, I'm going to pause for a second. Raise your hand if you feel like you're comfortable that I'll repeat this. Just are you comfortable that the bullet would reach a height of 45 meters if the duck is not involved in this problem at all? The bullet of its own accord, just by physics, should reach a height of 45 meters and then fall back down. Raise your electronic hand if you're comfortable with that. Oh, I think I've lost everything. Okay. Raise your electronic. Okay, thank you, Karen. Thank you, Scott. Okay, quick save, quick save. Okay, for real. I mean, this would be okay. Cool. Okay, it's a little sus, ladies and gentlemen. But okay, no, fine, fine. If you're good, I'm good. But again, that's just you. And if there was a little bit more time, well, you know what? Oh wait, Joran, that's a yes? Okay. You know what? Because we're on track, and because I do feel like maybe I'm talking so much, I'm losing people. I'm going to do something a little bit obnoxious here. We're still going to finish this on time, I promise. Okay. And for those of you who really are paying attention, or you want to make sure that you're with me, I'm going to add one page right now. Hold on. So you want to pay attention. I'm going to give you a little practice problem to do right now. You're going to do it in the direct chat. Just like in the video when we did that. I'm going to just do a fast one just to make sure we're all okay. Because this is all good practice for the exam, I promise. Wait, how do we add a page? Hold on. I promise I'm watching the clock. You won't. Okay. Okay. Very quickly now. Hold on. I'm just gonna move this. Is this? Yeah. Okay. All right. Very quickly now. Do this one in your head. And I'm not going to spend a lot of time, but just for practice, try this in your head. I'm not going to respond to everybody in direct chat, but I want in the direct chat either put an answer to this, and then you can submit for points that are whether you got it right or wrong. Put an answer to this, or put I am paying attention, but I can't do it, or something like that, or something like that. And I'm not going to dwell, but just for your own sake, for practice, you should try and follow the model of what I just use this as a checkpoint, whatever. I'm telling you, you should be able to do this in your ultimately. Like maybe you can't yet. I'm not trying to scare you, but this is like one of your goals for when we get to exam time. Like you should be able. So pretend the shot was just fired up at 50 meters per second. Everything else the same. And again, we don't care about the duck. Just how high would it get in that time if it were fired up at 50 meters per second? And so either put an answer or just put I'm paying attention, but this is too hard, or just something. And I'm not going to, just so I know where we are as a class. So I'm going to pause. So I'm going to wait till I get a bunch of answers in the direct chat, not a million, but a bunch. Or if you have to put in the chat, I don't understand the question or something, I'll try to repeat it. But okay. Okay. You're being honest. All right. I'm seeing in the direct chat. Keep going. More in the direct chat. Oh, okay. That's good. Some people are asking for more time. That's fair. I'll give you a little more time. Okay. Okay. Some people are asking for more time. That's good. So I don't want to yell while they're thinking. But my what I'm trying to say is, well, what I'm asking right now is just imagine throwing something up. It's like a practice problem. Forget the duck, forget all the details, forget the shot. Just imagine you throw something up. Like it's just this. Here's the question I'm asking. As a sidebar practice question, I'm literally asking if you threw something up at a rate of 50 meters per second, but gravity was producing a downward constant acceleration the whole time of negative 10 meters per second squared, how high would this thing get before it started falling back down to where it was thrown from? That's what I'm asking. And I'm telling you, and I'll tell you the answer in a second. But I'm telling you, number one, what you want to realize is that's exactly the question I just asked about the bullet going up to the duck. I'm trying to emphasize that the big old duck looks hard because there's all these different parts to it. But each part is just an independent physics problem that you need to know on its own. That's why it's like a good review practice problem. All right. And what we just were solving with the shot, we were basically just asking ourselves, how far would the shot get up by itself if there was no duck involved? Now, I'm telling you that kind of problem, by the time you take an exam, you should be able to do in your head. So I see that a bunch of people said in the chat, like, so that's the question. You should, okay. So a lot of people are being honest and saying in the chat they can't do it. So, which also means I think this is worthwhile that I'm redoing the duck. Like, hopefully I'm not wasting your time then talking about this whole duck problem now, even though it was talked about in the videos. Now, there's still only 14 minutes left, so I can only say so much. I will tell you, even this, you could solve it by plugging into the 1 FAT squared equation and stuff like that. But I'm telling you right now, okay, I'm telling you that where you want to strive for, you want to take notes on this or replay this video or stuff like that until you can get yourself to the point of realizing that to answer this question that I'm putting right here, and I'll be honest, like a lot of people are saying in the chat that they're paying attention and saying they're with me, but they can't answer it. The truth is, not one person yet has actually given an answer in the chat. So it's okay. I mean, you're paying attention. Good. It means this is worth your time. But I do want to let you know that eventually you want to be able to do this. Like this is something to think about at home before the problems get any harder. So I'm going to say it once now, but you're going to have to think about it at home because I do want to obviously finish the. But of course, the big old duck is hard if each piece is hard. Okay, is time involved? Okay, so is one person just going to put an answer in, which I'm very impressed that they put. I will admit that the one person who's put in an answer, it was very thoughtful, good answer. It's not the right answer, so I think everybody's getting something out of this. It's not a, and you can also submit for points. Someone asked in the chat, "Is time involved?" Well, good point. Good observation. I'm not telling you the time in the phrasing of the question, but I'm asking you, how far will this thing get to get to a peak height? So what I tacitly believe is, in order to get that, well, you either would use an equation. One way you could solve this if you just wanted to blindly plug into an equation, you could plug into the one equation that doesn't involve time at all and doesn't solve for time. You could plug into the equation x equals v squared minus v naught squared over 2a. This is a one kind of, if you wanted to blindly, but you wouldn't like learn a lot, but it would be practice and it would get you the right answer. But what I really recommend here, oh, great. I want to say the one person just put in an answer and it's correct. So for, and this is not a competition. I'm not trying to shame anybody. It's a checkpoint. Um, but if you did get an answer, good for you. You could blindly plug into the one equation that has no time in it, because you're right, I did not tell you the time. So you could plug into x equals v squared minus v naught squared over 2a. However, what I really recommend, and then I'm watching the time, I want to get back to the problem here. What I really recommend is you break this down into very good. Another person just got the right answer. Hold on. I also don't want to get I have to watch the clock, obviously. I'm just looking. Okay. So I'm going to so what I recommend for this, I'm going to say this once, replay this later, whatever. And everything I'm about to say could be seen in equations. Like I explained a minute ago, I'm not going to say the equations now. You have to do this for review. But I'm saying if the thing is thrown up at 50 meters per second, then in order to get to a peak height means run out of speed, get to an instantaneous velocity of 0. So it's got to get from 50 to 0. Well, it's losing 10 every second. According to gravity, it's losing 10 every second, according to what it says right there. That's a negative sign. So in order to go from 50 to 0, losing 10 every second, it would take 5 seconds. 50 divided by 10 is 5. So the time to get to a peak height, you can just realize, is 5 seconds. So it's going to take 5 seconds to get to a peak height. So all I need to know if it's going to travel for 5 seconds is what's its average velocity for those 5 seconds. Well, its average velocity would not be 50. Its initial velocity is 50. Its final velocity is 0. So on average, its velocity is 50 plus 0 divided by 2, i.e. 25. So for this problem, this practice problem I'm doing right here, what we have the equivalent of something traveling on average 25 meters per second for 5 seconds. This thing will travel 125 meters. That's the answer to this practice problem. And think about it later, but that's exactly how I just got the answer to the problem we're actually working on. Well, we had the same situation, just different numbers. We had something thrown up at 30. I'm saying if you throw something up at 30, the shot in the big old duck problem, if you throw it at 30, then it's going to take 3 seconds and on average go for 15 meters per second. So it's going to reach a peak height of 45 meters. Now, why do I even care? I'm saying that even if the duck isn't there, this shot is going to make it all the way to 45 meters if the duck isn't there and then start coming back down. The duck is there. The duck is at a height of 40. So think about this. This thing is going up to 45 meters. And then it's going to, at 45 meters, it's going to start coming back down from 45. It's got 5 meters to travel to hit that height of the duck. Remember from the videos and from practicing, in the first second of free fall, if you're understanding constant acceleration and you're reviewing, you'll see that in the first second of free fall, we always fall 5 meters. We don't fall 10. another checkpoint. You want to understand this. In your first second of free fall from rest, you fall 5 meters. So this thing is 5 meters above the duck. If you think about it, it makes perfect sense. It would take, in other words, I'm saying the 2 and the 4 answers for time really do make sense. 2 and 4 really make sense, even if you don't understand quadratic equations and all that, because 3 seconds is the amount of time it would take this thing to go all the way up to 45 meters. So it's either going to hit the duck exactly 1 second before the peak, or it's going to hit the duck 1 second after the peak. It's symmetric. 2 and 4 perfectly surround 3, as they should. There's no more other ways I could say it. You just have to think about it at home. But this would take 3 seconds to go up to 45 meters, but we're only asking it to go to 40. So it's either going to hit the 41 second before 3, or it's going to hit the 41 second after 3, i.e. 2 and 4 are the 2 different times that the shot would be at the height of the duck. Now, I spent a lot of time on that because that's like the hardest part of the problem, I think, the main part to conceptualize. Once you realize that there's 2 different times that the shot could be at the height of the duck, now we go to the other axis. We have 7 minutes left. Now we go and look at the duck. The duck, we're going to apply the same equations to the duck, 1f(at) squared plus v naught t. It's just now we're going to use the time that we solved from the y-axis and plug it in to the x-axis, because the whole premise here is the duck will be traveling for that same amount of time. The total amount of time that the shot is in the air is the total amount of time that the duck will be traveling. And we're going to use the same equation, 1f(at) squared plus v naught t, to apply to the duck, only the acceleration is going to be different for the duck. It's not gravity anymore. The duck is moving horizontally. Furthermore, an extra detail of the problem, it's just a detail, it's an annoying detail, but it's just a detail, is that the duck, it turns out, has 2 different segments to its horizontal motion, kind of like homework 1B, back in our very first homework, when an instructor went one constant velocity, and then went a different constant velocity, and then went a different constant. So each different constant velocity was a different segment of motion that we sort of started over the equations. Each new constant value we plugged in for that segment. Well, here, it's not constant velocities, it's constant accelerations. For the first half of a segment, call it for the first half of a second, call it segment A, the duck is traveling with an acceleration of 0. It's a constant acceleration of nothing, of 0. So I can use the equation 1f(at) squared, plug in 0 for A, and that reduces to the simple idea of displacement equals average velocity times time. The average velocity is the constant velocity, is the initial velocity. They're all the same because they're not changing. There's no acceleration. So for the first half of a second, this says, for the first half of a second, the duck travels 10 meters, definitely. In segment A, the duck travels 10 meters no matter what. So the duck has to be back at least 10 meters no matter what. But then the duck starts accelerating. So now it's going to accelerate for a certain amount of time. What time? Well, either the amount of time that it takes before it hits an upward shot or a downward shot. So let's do them one at a time. If it's traveling up, if I hit the duck on the way up, I have 4 minutes to do this. If it hits it on the way up, I'm plugging in the time I got. I'm plugging in one of my values for time, but notice I'm not plugging in the whole value. This is a detail. Note. I'm saying if you hit it on the way up, we've got a total of 2 seconds. If you hit it on the way up, the shot will take 2 seconds before it hits that height. So we've got a total of 2 seconds to play with. Well, already 1/2 of a second has been used up by the duck not accelerating at all. So there's 1.5 seconds remaining. So we want to find out how far the duck will go at its acceleration rate of 16 in the 1.5 seconds remaining. This is where I may have made a mistake in the video, right? But I'm just plugging in now 1.5 seconds squared times acceleration of 16 times 1/2 plus initial velocity of 20 times 1.5 times. In other words, well, I can't explain it anymore, but if we're figuring it out, how far the duck travels in the accelerated portion of its motion for the remaining time on the shot's way up, I plug in 1.5 and I get that the duck would travel 48 meters just in the accelerated part, 48 meters according to that equation. But then we've got to add in other words, this is segment B and this is from segment A. So I add them together, and then strictly speaking, that means the duck will travel a total of 58 meters, if it's to be hit on the way up. Total of 58 meters, 10 meters for its unaccelerated portion, and then the remaining 48 meters for its accelerated portion. If I want to hit the duck on the way up, the duck has got to be placed back. The duck had to have started back at negative 58 meters if I'm hitting it on the way up. If I'm hitting it on the way down, same logic, but I plug in 3.5 because 4 minus 0.5 equals 3.5 seconds, right? 1/2 a second's already been used up for the unaccelerated portion. So I plug in 3.5 squared, same acceleration, same initial velocity. So the equation gets me 168 meters. That's for segment A. For segment B, the plus 10 for segment A. So there's a lot of details here, but it's one big concept. So I add 98 to 68 and I get, is that right? 168 plus 10. So I get 178. And then I technically put a negative sign on it, meaning that the two possible places, so the answers, the two possible places that the duck should be placed are either at negative 58 meters. I believe these are the correct answers, even if the video said something else. That's why I'm correcting it now. The duck should be placed to the left 58 meters if you want to hit it on the way up, or to the left 178 meters if you want to hit it on the way down, right? You have to be placed back farther if you want to give it, the bullet time to go all the way up and come down to hit so those are the two possible answers to the big old duck problem, and that's how you solve it. So, and there I could stop. I'm going to stop. We're good. You've been very attentive. Please review all this stuff. You could start Wednesday with more questions about this. I will be in my office tomorrow at 11. And if you want to text me to find out where my office is or whatever, anyway, I'll be there if you want to ask more questions. But that's the end of class. Have a great night. I'm going to hang out for a minute. If there's any questions or issues at all, I'm going to turn off the recording. Okay, I'm looking at the chat. So I'm not going anywhere, but you can. All right, hold on.